Yeah, so as you can see, our talk's on the scalability and performance of the AMWA IS-04 and IS-05 NMOS specifications for network media. We were trying to go for the prize for the longest presentation title there. I don't know if we made it or not. But, I'm Rob Porter. My colleague is Gareth, Sylvester-Bradley. We both work for Sony Europe Limited in the UK. So just to start to put the talk in context, John's talk led into this very well, actually. So what we're talking about is, as John called them, engineered facilities or broadcast facilities that are operating with the SMPTE 2110, ST2110 suite of standards. And these, as many of you will know, define the protocols for the transport of the media essence around the network. And the key thing with this is that the different media essences make up separate streams on the network. So the audio, the video, and the metadata or ancillary data are separate streams over the network. But how do we go about recognizing a new device that we plug into that network? How do we go about controlling the connections between devices on the network? And this is where the AMWA, that's the Advanced Media Workflow Association, network media open specifications come in. So this talk focuses on two of those, interface specifications IS-04 and IS-05, and these define the protocols for the transport of, for the discovery, registration, and the connection management of the media devices on the network. They take the form of RESTful APIs, so they use operations such as HTTP post, put, patch, and get, and also WebSockets for the notifications of changes. What we wanted to do was to prove that we could use these kind of APIs at scale. So these HTTP-based APIs are typically used on the web. We wanted to prove that within a media network, we could use those at scale without causing any problems. So this is why within the AMWA, we set up the AMWA NMOS Scalability study, and Sony have been leading that for a number of months now. And we want to make sure that we can use these APIs successfully across many, many thousands of devices that are typical of very large real-world deployments. The idea was then that we'd report back to the industry, and that's what we're doing today. So I'll start by going into what IS-04 and IS-05 are in a little bit more detail, how they work. I'll then talk about our test environment that we've used for the scalability study. And then I'll hand over to Gareth, who'll talk about some of our results and give some of the kind of best practice recommendations for how to use these APIs at scale. So we're centered on the network, represented here just by a single network switch, but of course that could be many. And with IS-04, the key thing here is we add an NMOS registry to our network. So in fact, we have a registration and discovery system, an RDS, which could comprise several registries. And what these are doing is these are allowing media devices to register to the network. Each of them includes a database that stores all the registered resources on that network. And the RDS exposes two APIs, a registration API and a query API. We can also add some NMOS nodes to the network. So these are kind of the endpoints. So an NMOS node, as it says here, is a logical host connected to the network. And it can host one or more NMOS devices, each of which can have any number of associated senders, receivers, sources, and flows. And each of those terms in bold is known as an NMOS resource, and they're defined by the JTNM content model. So as an example, this NMOS node here is an IP-connected camera. That comprises two senders, a video sender and an audio sender, and each of those has an associated source and a flow of the data it makes available on the network. The camera also has two receivers, and that could be two return channels back to the return video channels back to the camera. Another example here is an IP multi-viewer. Again, this is all represented by a single node. This time, we've represented each picture-in-picture segment within that multi-viewer as a separate device within that node, whereas the camera was represented by a single device. And each device has 3 receivers, an audio, a video, and an ancillary data receiver. When we connect a node to the network, the node starts by discovering all the registration APIs that are advertised over DNS service discovery. And that could be either multicast or unicast service discovery. We'll talk about that a little bit more later. The node then selects a registration API by selecting the one with the highest priority. And that will then register its node resource, that's the top level resource with the selected registration API. It will then go on to make several more calls to the registration API to register each of its sub-resources. That's the devices, senders, receivers, sources, and flows. At the same time, it will begin to post regular heartbeats to the registry. If the registry doesn't receive these regular heartbeats, it will expire the node from the network. So that's its way of keeping up the registry, keeping up to date with what's attached to the network. So what does one of these API calls look like? We want to know what we're measuring the scalability of. So it looks something like this. So this is a registration API request for the node's initial registration. It's basically making an HTTP post request to the registry with a bunch of JSON there, just a few bytes of data. And that JSON contains information such as the name of the node and also its interfaces that are available over the network. And the registry then responds with a response that it's been successfully created and gives a URL, an endpoint for that node within the registry, which can be used if you want to. Over the registration API, it can be used for debug, or it can be used to actually delete that node from the registry. The heartbeats are a little bit smaller. These will typically happen every 5 seconds. That's the kind of default that's been recommended. That's just a post to the health resource on the registry, and the registry will respond saying OK with a timestamp. The registry will expire the node after an expiry interval, which is typically set to 12 seconds by default. That's the kind of recommendation. So once we've registered our first node, we can attach all the others to the network and have them also register over the registration API. And then what about if we want to start making connections between the nodes? Well, we can start by attaching an NMOS client to the network. So an NMOS client is a controller, something like a broadcast controller or a routing panel. And that needs to know what's attached to the network. So it can talk to the registry over the NMOS IS-04 query API and get a list of all the registered resources that are available on the network and populate its UI. If it wants updates of what's been attached or removed from the network, it can also subscribe to WebSockets, and then it will get notifications of all the changes that have happened within the registry and discovery system. So on to AMWA IS-05. So this is for connection management, whereas IS-04 was the discovery and registration. At this point, we know what's on the network from the registry, and so we no longer need to talk to the registry. This IS-05 is all about talking to the nodes directly and setting up connections. So when you want to make a connection, you can first of all get the transport file from the sender. The transport file is typically something like an SDP file, and it can contain information like the format information, but also critically the multicast address that sending node, that sender, is streaming its data on. The client can then patch that transport file to the receiver, and so the receiver now knows what multicast address to join in order to start receiving packets. And it can do that using something like an IGMP join, and then it will start receiving packets over the network from the sending node, and hopefully you get a nice picture on your receiving node, in this case, if it's a monitor. So this slide just gives a summary of all those APIs. The eagle-eyed of you will notice there's one that I haven't mentioned. That's the IS-04 node API. So this is really only used if you don't have any registries attached to your network. It's used to operate in peer-to-peer mode, so the nodes can talk to each other directly and set up connections between themselves. The nodes will default to peer-to-peer mode if they can't find a registry on the network. So the testbed we've used for this has involved using our own open source implementation of the NMOS Registry and node, which is freely available on GitHub if anyone wants to try it. It's an Apache 2 license, so it's open to use by everyone. We've also tried some other implementations that are also available as open source, just to check that our results tally with other implementations, that we get similar results. The study makes use of a virtualized network, and we felt this was valid because it's the APIs we're testing, it's the control layer. We're not testing the transport layer, we're not trying to send media over the network, so actually using a virtualized network and just making the calls to the registry and the nodes within that virtualized network seems to be a valid thing to do. And within that virtualized network, we can then make timing measurements of various operations at scale. So the virtualized network we chose to use is called Mininet, which is also open source software. That runs within a Linux virtual machine. It can be physically hosted on a computer running Windows, Linux, or Mac operating system. What you can do within Mininet is you can set up a network topology, however you choose, with any number of switches. You can optionally have a network controller there. Attached to each switch, you can have several Mininet hosts, which are a bit like lightweight containers with virtualized network interface cards, virtualized NICs. And on each Mininet host, we've chosen to run separate NMOS processes. So we typically have a registry running on the first host and nodes running on all the others, and then we can make measurements of things like all the nodes initially registering with the registry. We do that by accessing the registry logs using a custom plugin for Logstash, which then populates an Elasticsearch database and is able to drive a Kibana dashboard, which gives us nice real-time graphs of things registering onto the network. So this is a good point to hand over to Gareth, who will explain some of the results.
Thanks, Rob. Yeah, so I think the only thing to add to that explanation of our test environment is that although we've done some NMOS specific enhancements, NMOS specific commands within the test environment, you've got the full power of Mininet underneath. So you can vary the topology, you can change the number of virtual hosts, the number of switches and how those are connected, have multiple links, redundant links and so on. And you can bridge to outside hosts as well. So for instance, one of the things we've done with Mininet is to be able to bridge to the BBC reference implementation of the NMOS registry running in another VM. So it's a flexible environment. We can script the environment. So Mininet has its own interactive command line, which you can use the Mininet commands on, both the built-in ones and our extensions. And you can run a shell on every virtual host in the virtual network. And on top of that, there's a Python object model where you can manipulate the network object entities. As Rob said, the registry and nodes we're using are our open source implementations, which we and others are building products out of. So it's a good test bed for tuning these things. And some of the results I'll talk about today are maybe us fixing our open source software as we go. It's been a great test bed for that. As well as the supporting the NMOS APIs, all of this software supports common log file formats so that we can do this interaction with Logstash and the dashboards. And as well as that, a logging API in the style of the other NMOS APIs, which gives us some other flexibility. So all of our test scenarios that I'm going to talk about were run on a single desktop PC, and the Mininet VM here was given 12 cores, 40 gigs of RAM to play with. And as Rob said, we reiterate that we're only testing scalability and redundancy of the control APIs, not of the data network. So, as both John and Rob talked about, one of the key measurements is what happens at power on. What happens when we turn on everything, we've had a power failure, or we're starting up a new system? How long does it take for everything to be up and ready to use? So we've used our test environment to simulate node networks of up to 4,000 nodes with 10,000 or more senders and receivers. But typically, we've been testing up to sort of 2,500 nodes. And 6 resources per node, 15,000 resources on the network of the senders, flows, sources, and so on that we've talked about. What you can see in this chart is that the time taken to register is kind of linear, really, in the number of nodes in the network. Kind of makes sense. But the result here, and this is our kind of initial findings, show that 2,500 nodes takes a little over 3.5 minutes before the system's fully ready to use, and so on, which maybe is a little disappointing. Luckily, because we have the dashboards that we're using, we can kind of drill down into that. And so for one example here, where we're talking about the 2,500 node case, we can see that that 3.5 minutes is actually made up of a kind of a slow start and a kind of long tail as the last few nodes are added to the registry. And that's seen in other sizes of the network as well. So here's a case with 750 nodes, and to be honest, we're impatient people, so we've stuck to this kind of size system for most of the results that you'll see, but they scale to the other sizes we've tested. So, looking at this, we drilled down into what that slow start and long tail were about. And the first thing, as John mentioned, was to do with MDNS service discovery, and the MDNS daemon that was in use really being overwhelmed at power on. That kind of went into the nodes dropping back into peer-to-peer mode at that point when they couldn't find a registry, and then sitting there and polling only infrequently for a new registry. So there's this kind of slow start as the network's overwhelmed to start with, and then nodes pick up. At the other end, once things have mostly registered, we've got 1 or 2 nodes who have lost connections, and at the software level, it's not always obvious what errors are going on, and so they've ended up timing out HTTP requests. And by default, the software that we were using was only timing out requests after 30 seconds or a minute. So if they were late getting in there, there's this long drag before they retry operations. So what we've been able to show is that by, as John said, I think implementing the standards properly and being able to tune these things, we can do much better. So what we've got here is having implemented an exponential backoff capped to a sensible value for the startup, for both MDNS and for initial interaction with the registry, and also reducing the timeouts on HTTP requests to kind of match the expectation in the NMOS APIs of the timeouts that Rob and John have mentioned. We've gone down from this 750 node case to taking under 30 seconds from over 50, and that was equally true in the 2,500 node case, where we've gone down from 3.5 minutes to around 2 minutes. One of the other parameters that's tuned is the heartbeat interval, expiry interval that Rob's mentioned, and there's a trade-off there between the frequency of communication over the network and the load that places on the network and on the registry and so on, versus how long stale information hangs around in the registry, how long nodes take to notice registries have failed or connections have failed and move to another one, particularly in the case of kind of resilience really to short-term link failure. What we found was that even across a broad scale, actually the default values that are in the spec, I guess they're there for a reason, those default values work pretty well, 5 seconds. If we cut the heartbeat down to a second or less, as we've done at several interops and proved again in our simulated environment, although things are noticed quicker, actually things like the initial registration test take a lot longer. You go back up from 30 seconds to 40 or 50 seconds for a case like this. On the other hand, increasing it so that there's less traffic, actually there's no improvement there. So those default values work. One of the other things that's suggested in the IS-04 specification to improve redundancy and performance, scalability, is to use multiple registries, and in particular federated registries, so that all resources on the network are discoverable whichever one the node is talking to. We have an interest in this, and we've been looking at different replication strategies, and we've settled on a optimistic strategy as having highest performance and done some tests with that. And versus the case we were just talking about with sort of 30 seconds to register these nodes, surprisingly, running 2 registries federated, actually we do see that the performance is twice as quick for that initial registration. So that's a key part of scalability. Another discussion that's happened in AMWA during this sort of open development of these specs is whether we need a bulk API for registration. As Rob said, you've got to make 6 requests for your 6 resources. You've got to make 20 requests for 20 resources. So would a bulk API speed things up? So we did some tests with varying the number of resources managed by each individual node as a kind of placeholder simulation of that kind of change. And we do find that there is a linear relationship with the number of resource requests, registration requests that a node is making and the total time taken to register. But on the other hand, we're still talking here about 15,000 resources across a small number of nodes being much quicker than with 2,500 nodes managing the same resources. Things like connection reuse in HTTP and HTTP keep alive are really important for keeping things moving quickly. So I think we talked about some recommendations for best practice. Make these timeouts and retry intervals configurable, set them up for your deployment, implement the whole spec, and consider using clustered or federated registries, and definitely look at using unicast DNS service discovery as well as the multicast option. There are other areas. There is just 1 or 2 more up there. We do, all these interop events, be testing this thing with 60 vendors and often more equipment from vendors. So these things are getting tested in real-world networks as well. One thing that we haven't done a lot of yet, but I think is going to be quite important, is the testing with topologies with redundant switches and redundant links. And the nice thing is that the Mininet environment being open, that's something that we can take forward, and so can anybody else who wants to have a look at it. Our paper mentioned that we were preparing connection results, so this is new for you guys. Thank you for coming. So we have done just relatively recently some simple emulation of a broadcast controller in the Mininet network, and able to show that a broadcast controller can populate itself from the registry in less than a second, and that then we can make 750 cross-point changes in only 2 or 3 seconds. So that looks pretty good. What I would say was that our naive first implementation took nearly 10 times as long. And the reason for that is how you use these APIs. You need to make use of the caching of results where that's possible in terms of fetching transport files. You need to use concurrent requests where that's possible, or pipeline requests, and take advantage of the paging supported by the APIs and the push notification that the IS-04 specification allows. Right. I have a quick demo which just shows that this stuff really is using. You're going to see the dashboards on the left and the Mininet VM on the right, and just very quickly going through a test. You probably can't see what it says, but we've got a very short command line to launch Mininet, and then it's gonna fire up our virtual hosts, create the virtual links, hook them up to the switches, make those run standalone, fire up a registry and a number of nodes. And while that's all happening, in the background, the dashboards are just monitoring the logs through the logging APIs of these nodes on the network. So as soon as the nodes start up, you can start seeing the registry events. At the top, we've got a dashboard showing the number of registered resources in the registry. And then once they're all registered, you can actually see the heartbeats start to happen. So there's on the second graph, which is simply showing the number of events happening in the registry, we can see that heartbeats are kind of ongoing. So if we then do a cross-point change and connect 255 receivers randomly to 255 senders on the network, we can then see the connections take place. And again, that's just done in a few seconds. So all of this is interactive, but it can be scripted, and you can do what you like with it. Please do go away and do things with this. Okay, I think that's it for us. Thank you.
Thank you for watching. If you enjoyed this video, please tap the like button and also subscribe to our channel to receive notifications when we add new content. For more information about us, please visit SMPTE.org. We'll see you next time.